Yeah, I run the team that does a lot of our great data structures work. And not all of our data structures work. Data structures are kind of everywhere, but IPLD is really like the lowest layer of the interplanetary stack. It sits beneath Filecoin, it sits beneath IPFS, and it's really like how we think about creating data structures. So that's what I'm going to share. This is kind of like a clips show of like all the best talks and slides that people have created lately. So there's going to be some variation in format, but it should be like a really fun time. Okay, so let's dive right into it. What I'm going to talk about, the sort of whole class of data structures that we're talking about when we talk about building stuff for Filecoin. We're talking about these things called DAGs. If you've been around Filecoin enough, you probably heard people say DAG a lot. DAG stands for Directed Acyclic Graph, which is a very fancy way of describing this data structure that is really useful and kind of wraps up the whole category of data structures that you create with hash linking. So when we talk about content address data structures, we're talking about hash linked data structures. You can think of DAGs as, if you come from trees and B trees, you can think of it as a tree that allows you to reference common branches and leaves from other nodes. So basically a tree with deduplication. If you come from graphs, you can think of it more as graphs that don't have circular references. You're not allowed to have circular references. But the idea is that it's a graph, but all of the links have to kind of direct one way. There's a lot of different visualizations, but I actually like this one up here the best because while the links are going right to left, and that may seem weird, it's actually really in the order that you would create this data structure. So you would start with the node on the left and start to work your way right. Because in content address data structures, in order to link to something, we have to have the data so that we can create this hash-based link. So the first thing you create is that one that says G, and then you create everything else up from there in whatever order makes sense. So in IPFS, we have two main DAG layouts that we use just for the files. One is called a balanced DAG and one is called a trickle DAG. So when you import a file into IPFS and you get back this identifier, that identifier isn't a hash of just the file data. It's actually the file data broken up into parts and then assembled into one of these structures. So you can kind of look at it like this, where you have the actual data as streams of different binary values, and then they're all linked together with this structure. IPFS actually uses IPLD for that. IPFS was created, and this was created actually before IPLD was broken off as a project. We were sort of like an arm or a leg broken off from IPFS itself. But like our whole layer here and how IPFS thinks about this it's all IPLD data structures. So here we have like just a file with two chunks. And then that file is inside of two directories. And so those directories just link down to the file, right? When we want to append data to that file, what we do is we create a new chunk, and then we create a new file node that links to all of those chunks. And then we go and recreate those directories. So now we've actually orphaned some blocks here. So if we were pinning this old directory and then we stopped pinning it and we pinned this new one and we told IPFS to GC, it would actually remove those three blocks. They're not necessary anymore. And that means that if you want to track the history of changes over time, you might create a data structure that actually links between these two things and says, oh, I'm going to track this directory over time and I'm going to keep linking to each part. Getting block data into IPFS, getting data from IPFS into Lotus is documented here. Don't read this slide, just go to the link. This is being improved all of the time, and so you should really go to whatever the current reference is for getting data out of IPFS into Lotus. But the important thing to note here is that any data that you get into IPFS, you can get into Filecoin. You can take any graph of any data, not just files from IPFS, and you can get them into Lotus. The example at the bottom here takes actual file data, it gets back an identifier, and then use that identifier in Lotus. That identifier is called a CID, or a content identifier. I don't have time to get into the entire structure of CIDs. That's literally like an entire other talk. But if you want to go and look up some stuff about this, there's a great protoschool tutorial called Anatomy of a CID that you should go check out and just learn how these content identifiers are made and how we really separate a lot of the concerns, and we have a lot of future proofing in these identifiers. So they really do become like the URL of Web3, the URL of a content addressed data layer for the internet. Let's dive right in though now. Let's have some fun. Let's like create a little DAG. So first we start with our first leaf node. So this is just some data, like a little hello world object here. And that's going to get a hash-based address. So this is what that looks like in JavaScript. We import this block API. We decide which hashing function that we want to use. Just use SHA-256. You'll have a good time. We're going to import a codec. We suggest that you use this codec that we create in IPLD called DAG This is actually also the codec that Filecoin uses internally for its own internal chain. But you can use it for creating whatever myriad data structures that you want to create, and we really recommend that you do that. Yeah, so you take that data value, you create a block, you get this new block instance, and then that block is going to have a couple things. It's going to have the bytes, so it's going to have the encoded binary data of that sort of DAG call, that DAG encode, and it's going to have an address. It's going to have the CID associated with it, and that's really all that we need to store this in IPFS, or frankly, to store it anywhere. We could put it in S3. We could put it in any key value store. Like this is enough right here. So let's actually start using this a little bit. Let's create a node that links to it. So we're going to create a little object called foo that's just going to have a value that actually links to this data that we just created. So what that looks like in JavaScript is you're just going to take that CID and you're going to use it as the value in another object that you're going to encode. It's really that simple. But it's not a DAG until we're doing some deduplication and creating a graph. So let's create another object that has another property and some other information in it and a link to that initial one, and then a new root node that kind of pulls all this together. So that's what this looks like. We're using the CID again as another link in another structure, and then we're taking both of those blocks and creating the root block now, this DDD block that links everything all together. And now we have a little DAG. We have a little tree structure, and the structure of this we can do different things with that. We can create indexes. We can create relationships. We can, describe whatever we need to describe in the world so that our applications can function. Then we just need to get these blocks into IPFS. This is a little tricky to do in a talk because there's so many different ways of running IPFS that you can't really lock in one way of getting block data into IPFS. One thing that I will say is that every way that you can run and use IPFS has a block API. So you can see the main sort of HTTP documentation in that first link. There's a how-to on how to work with this kind of data. There's even sort of like an IPFS Lite in Go that just serves these block data, doesn't do all the extra file stuff that's out there. It's really just working with these kinds of data structures. There's really myriad ways of getting your data into IPFS, but just use the block API, it'll be fine. And then once it's in IPFS, you can obviously get it into Filecoin. On the right here, this is just an example from a little project that I wrote. I'll talk a little bit more about it later. It's a little key value store that works on top of IPFS. And you can see that it's really only like 5 lines of code here in 2 functions to take that interface that we were using before to create those blocks and just wire it right into IPFS. So it's really, really easy to sort of plug that storage layer in once you're building data structures this way. Okay, I'm going to get into some concepts now. I'm going to talk a little bit about mutability. So here we have 2 directories, one directory inside of another, and then a bunch of different files, okay? So content address data structures are all immutable. You can't actually change them. If you change them, you'll get a new address. And so what do you do when you need to mutate things? When you mutate things, you basically just create a new immutable state that you arrive at from some mutation over a prior immutable state. So in this case, we wanted to change the first file in this to a different file. And what we did was we had to create now a new directory that links to all the same things in the root node and links to this new file object now. And so we've effectively orphaned that old root block and that old file, but we've kept all the other data in this tree now. And now we have a new root address, and now we need to broadcast that and move it around or store it in Filecoin. Want to get into some data structures that start to do more operations on top of all of these primitives. This is a very simplified version of how Git works. So you have these trees. You can think of them, for the purposes of this, you can think of them as just like the file structures in IPFS. Not really in Git, but we'll pretend. So you have these different trees of just the whole repository state, right? So all of your code files in your Git repository, they all look a certain way at each commit. So what you do is you create this commit message that has all the metadata about that commit, and it links to the whole tree of the file state at that time. And it links to the old commit that it was updating. So it doesn't link to the old file tree, it just links to the old commit, and from the old commit, it can get at the old file. And so as you sort of add new files and mutate things over time, you can see that these just keep linking back to the same commit messages each time. And even as they're updating these trees and getting new trees, all of this leaf data here, all these little blobs of data that make up your files at the very bottom there, those all remain kind of unchanged. And so that's why it's like a really efficient structure for maintaining this history, because when you change a file, you're only storing the parts of that file that you changed, and all the old references are staying around. So it's this form of deduplication that works really, really well when you're trying to maintain a history. When you have really complex structures, sometimes the insertion order can reorder some of the different elements, and you have a lot of other adjustment problems. There are a lot of reasons why if you mutate a structure like this and you get something else that's very complex, you orphan a lot of data, and you may not want to keep that data around forever. Not everything is Git, not everything needs to maintain an entire history. So when you're thinking about and you're starting to design these data structures that mutate over time, you need to think about what a mutation operation will do, not just in terms of the new blocks and new nodes that you need to create, but also how much data is being left behind. How much garbage are you essentially generating every time that you do this? And there are other considerations too, like, can I do bulk updates to the structure? If you can bulk all your updates together, you actually end up creating a lot less garbage in between. So there's a lot of different considerations to keep in mind as you start to design these structures and you're thinking about how to mutate a data structure over time. I'll talk a little bit about the HAMT, and then you should really just go use it. So a HAMT, a hash array map tree, it is a big map. So it could be just a few megabytes, or it could be terabytes. It could be petabytes. It could really just get huge. You can have millions of different values in these things. I think we have one somewhere that is millions or billions of values. There are HAMTs inside of the Filecoin data structure itself. The on-chain data structure actually uses these HAMTs. And what it allows you to do is just create a really large key space for a map. And so, if you were just, encoding a small map, you would just put that into one block. But once that gets bigger than what you want the kind of block size to be, you have to find a way to break that up. And then as you break that up, one of the problems that you run into in these decentralized networks is that you need the hash of the entire structure to be consistent, regardless of the insertion order of the values. So think about it this way. If you have a bunch of transactions to process and another node gets those same transactions, but it gets them in a slightly different order, maybe it was processing transactions and some of those people were closer to it. If you insert those in a different order, a lot of different data structures like your standard B tree, that will end up creating a different tree structure depending on what order that you manipulated it in. The really cool thing about a HAMT is that regardless of that insertion order, you can insert them in whatever order that you want. You can do these over time, whatever. If you have the same data in that HAMT, it will have the same hash address as anybody else's HAMT. So this works really well in these consensus-driven scenarios where you really need to ensure that everybody is arriving at the same value. Another really cool property is that the HAMT has really guaranteed performance as it gets larger. So you can really sit down and do the math and go like, oh, okay, well, as this gets bigger, how many hops am I going to be away? How many links do I have to traverse in order to get at a particular value? That stays very constant regardless of how big the structure gets. So that's also another really, really good thing to consider when you're using the structure. So like I said, in IPLD, we have a very detailed spec on the HAMT. We have an implementation that uses our new Go IPLD Prime code gen that actually uses this IPLD schema language that you see on the right to get up and running. And also, you can literally look at the Filecoin HAMT, the HAMT that we use in Filecoin. It varies a little bit from our specification because our specification allows for some optionality. You can actually change the hashing function that you use. You can change the bucket and some of the dimensions of the structure. So depending on your performance scenario, you may want to tweak those values a little bit. When you tweak those values, obviously you're going to get different consistent hashes from different people. So that's one of the reasons why Filecoin differs a little bit from our spec. It doesn't specify those. We don't want people in the Filecoin chain to try to change those values. They'll arrive at different hashes. So that's also documented in the spec, though, the Filecoin variations. And in JavaScript, there's a bunch of modules, one that just really implements the base algorithms, another that has really reusable utilities on top of that library. And then, yeah, I would really encourage you to just go look at this little library. It's not more than maybe 100 or 200 lines, called DKB. It's a decentralized key value store. And it's just this HAMT mapped on top of IPFS for storage, and then with some sugar on it to just make it look nice and make it really like fun to use if you're a programmer and you want a little key value store. So it's a really good example of how you can take some of these lower level primitives that can be kind of hard to get your head around sometimes, like all of these big hash map trees. And you can just kind of decorate them to make them really pretty and reusable by like many more programmers than people that want to nerd out about data structures. And Rust also has an implementation of the Filecoin HAMT that you can go check out if that's your language. Another data structure that I want to talk about, this one's so fun. This was like really, really fun to build. We iterated on this for a long time and made a lot of tweaks. It has a very recursive schema, and that's one of the reasons that makes it kind of so powerful. But this problem that we started to run into with IPFS and just generally, you have streams of data, right? And the prior talk was talking about video, right? And so when you get a video file, you need to break that up into chunks. The most efficient way to chunk that actually is to look at the keyframe boundaries and break each part into a different binary value for each keyframe. That way, if you seek in the file, you always seek to a unique data value, and you don't have to get an entire block in order to seek to the middle of it. It's really nice. Anyway, there are all different ways to like cut up files, and then just like in IPFS where we have that balance DAG and that trickle DAG, there are different ways to do the layout of those streams of data to give you different sort of performance profiles. And one of the issues with the way that we had kind of done that in the past is that if you came up with a new layout algorithm, you also had to write a new reader. And so all of the old code and all the old stuff that was already in production couldn't read the new data structures. So the thing about this flexible byte layout is that it really is flexible, like the name says. It allows you to lay out a stream of different binary values, and you can use them. You can mix and match inline binary values and links to binary values. You can really vary the structure based on whatever algorithm that you want to create, whether you want to do balanced or trickle or whatever. And there's just one unified way to read this data structure. So you only ever need one reader function. You can always get a stream of bytes out of it. So it's really, really powerful. We're working on sort of the next generation UNIXFS, the data structures underneath IPFS. And this is really like the data stream part of that data structure. It's like a really solid spec now. There's a JavaScript implementation that I'm using a few places that I'll show you in a little bit. But yeah, this is just like a really fun data structure that I encourage you to check out if you work with streams of bytes, or if you're just into recursive data structure schemas. It's pretty fun stuff. Okay, so I'm going to throw some more links at you, and then if we have time, there's one more piece at the end here. First of all, there are some products that are already written on top of IPFS that if your use case fits them, you should really just use these products instead of going and designing a bunch of new data structures like I'm trying to encourage you to do right now. So yeah, I mean, Textile, PeerGhost, and OrbitDB are all built on top of these primitives. They all store data in IPFS. If you're doing something that looks like it fits these use cases, definitely go and use them. And I mean, these are all open source projects. So if you're curious about how they're designing this or how they're doing something, definitely go check it out. I look at the Textile stuff quite a bit. They have some really great specs. They've done a lot of really good code work, and I poke at their code all the time to see what they're doing. And some of their folks have actually been peering into some of our new stuff as well in DAGDB, which we'll talk about now. We've also been building some new experiments. We'd like to take these data structures that we're building and start to actually assemble them into something like a database, something like what somebody would use, and then try to mature that into a project over time. And so these aren't ready for sort of production use, but they're really good to go look at if you're going to go design data structures or figure out how to take some of the data structures that I already talked about and put them into whatever application that you're doing. So DAGDB is like really a full-featured database. It does peer-to-peer replication. It has a very sort of Git like push and pull and remote structure. It has a secondary indexing system built on top of it. And one of the cool things is that this is really where like I take any of these new data structures that we're building and I start to see what they look like when we start to like actually build sugar on top of them. So as an example, in DAGDB, you can take any async generator in JavaScript, so any stream of data, and use it as a value that you plug into DAGDB. And what DAGDB will do is it'll go, oh, that's a stream. I'm going to go turn that into an FBL, and it'll store that as one of these flexible byte layouts that I just talked about. And then when you go and get that value out, it'll convert it back into an async generator that you can then iterate over. It's really cool. DKV, I talked about it a little bit before. Definitely look at that before DAGDB because it's much smaller. It's a really, really small amount of code, and it really shows you what it's like to build a little database on top of, with IPLD on top of IPFS. And unlike DAGDB, which has like its own storage abstraction layer, DKV is just on top of IPFS. So it's a lot simpler. Also, I mean, I mentioned before, Protoschool's fantastic. Go check it out. Anything you're trying to learn, if you see a tutorial on Protoschool, do that before you look at any of the other docs that we have. IPLD has a beautiful new doc site that we've been trying to iterate on and make better over time. You can go there to read about how to, use some of the code samples that I talked about before, but there are also examples in Go and in Rust, and a lot of sort of like a glossary of terminology and a lot of other just useful resources when you're getting started with using IPLD and building these data structures. And we also have a specifications website. The spec site is great. We have a really, really detailed specification and docs for our schema language. So if you're going to start to design a lot of these, I would really encourage you to look at the schema language, because as a design language for these types of data structures, it works really, really well, especially if you're in a typed language.
Awesome. Well, thanks so much, Michael. I gotta say, it's always tough to take a low-level primitive like data structures and make it approachable, and you do it just spectacularly every time. So thanks so much. Really appreciate it.
Yeah, you too. Thank you.